In this video, we're going to look at rational functions and figure out what these functions look like. And again, just as a reminder, a rational function means we have something that kind of looks like this. It has some kind of variable in the denominator, and that makes it rational, because when we're thinking rational numbers, we're thinking fractions. So our first question when we're trying to graph these functions is, what is this function going to look like? When you looked at the first objective, we looked at domains of rational functions. And our domain was everything except where a denominator is 0. And what that looks like for a graph is either a vertical asymptote or a hole. So let's say we have some kind of rational function. This is a pretty basic rational function. This one has a vertical asymptote at x equals 0. So you can see the function is doing normal function things, except as we get closer and closer to 0, the function either goes all the way down to negative infinity, or in this case, all the way up to positive infinity. So we see there's a really big issue at 0, and there are really weird things that are going on around 0. So in contrast, if I have some kind of hole, maybe the function looks like this and continues. So you can see we still have an issue at some value, but we don't really have an issue anywhere around that value, which is very different than this vertical asymptote. So practically what's happening? If I have a hole, that means in my equation, I had something like this. Maybe there are some more terms over here, and maybe there's some more terms over here. But the idea is I could pull out this factor. Right? I have x minus 1 on the top and x minus 1 on the bottom. This is 1. Except, oh, this is a bad example, but this thing, we have the same thing on the top and the bottom as 1, except where x is actually 1. So maybe for our example, let's change this to 2 so we know where all of our numbers are coming from. Right, so x minus 2 over x minus 2, it's the same number on the top and the bottom, and that's always going to be 1. It's not really going to affect the function, except where x is 2, because then it's 0 over 0, and our world implodes. We don't really know how to deal with 0 over 0. So with the ability to remove that, our function is everything that's left over. So we can see if we remove this issue spot, the function will act everywhere else normally. And that's why we're getting this hole. Otherwise, whatever's left in the denominator is going to make these huge breaks in the function, where the function is not going to be defined at that point, and it's still going to do weird things nearby. So let's do some examples. So we have our first example. Here we have a rational function. We have some variables in the denominator. And we want to determine vertical and or holes for this function. So we're going to start the same way that we deal with the domain of these functions. we're going to look at when the denominator is 0, because that is not going to be allowed in our domain. This comes back to all of our earlier modules when we were looking at factoring and solving quadratics. We need to figure out where this function is 0. So what I'm going to do, since these numbers aren't too large, we'll go ahead and look at where two numbers that multiply to be 10 and add to be 7. And if we go in order, we'll actually find it pretty quickly. Two numbers that multiply to be 10 and add to be 7 would be 2 and 5. So let's break up the middle term. And again, if this feels weird or you don't really remember how to factor, I would go back to that module on factoring and just kind of get a refresher, because we're going to be factoring a lot in these sections. So we see we can pull out maybe negative 2x to get x minus 1. Here we can pull out a 5 to get x minus 1. So we can pull out an x minus 1. We can pull out a negative 2 plus 5. So we can see these two values that aren't allowed in our domain are at 1 and 5 over 2. So now we think, okay, these are definitely not in our domain. Does our function have an issue just exactly there? Right? Is there a factor on the top and the bottom that we could pull out so that the function still works everywhere else? Or is the function going to have a huge issue there? Are these going to be our asymptotes? Now, since the numerator is just some number, there aren't any other factors. So these are both vertical asymptotes. And in this case, there are no holes. So we can have vertical asymptotes and holes. We could have all holes and no vertical asymptotes, or we could have some mix. There's no quick way to tell you how many of each we're going to have. So let's do another example. I think you guys would agree. This one looks a lot more complicated. So we're going to go ahead and start from the beginning. Just like before, I want to know where this is 0. Now this, we can't just factor normally. So what we'll need to do is synthetic division and just try to keep guessing at some numbers until we get something that works. So we'll write down our coefficients. I'm doing all of that in black because that's going to stay the same every single time. And now let's write down our possible roots. So we'll start with the possible integer roots. These will be the factors of our last term, the factors of 4. So plus or minus 1, plus or minus 2, plus or minus 4. Now, we have a lot more possibilities than that, but these integer ones are the ones that we're going to check first. Now, these other ones that we have, we get by dividing these possibilities by factors of 3. So not only do we have these, we also have 1/3, 2/3, and 4/3. A lot of possibilities, but again, we're going to start with these integers. So my normal suggestion is to start with something from the middle of your integers. So let's say 2 or negative 2. I'm going to just go ahead and try 2. 2 times negative 3 is negative 6. Adding down, that gives us negative 2, which gives negative 4, negative 1, negative 2, negative 6. So 2 didn't work. So we'll erase all of that. and maybe try -2. So now we get 6 goes to 10, goes to -20, and oh my, this is not going to work at all. So -2 didn't work. That's okay. Keep trying until we get something that works. So we've tried those two, so let's try maybe 1. That gets us -3, 1, 1, 4, 4. Woof! All right, it took 3 tries, but we found something that worked. And then at this point, we have -3x squared plus x plus 4. So we could factor this like normal, or we could continue to do synthetic division. I'm going to go ahead and factor it since this seems like it'd be pretty easy to factor. I'm looking for 2 numbers that multiply to be -12 and add to be 1. And I think there aren't very many options, so we can just jump to it. All right, -3 times 4 is -12, and those add to be 1. So I can pull out -3x. I can pull out 4. All right, and I was able to factor that second piece. So all of our factors, including that first number that we synthetically divided by, we get x minus 1, -3x plus 4, and x plus 1, which means the values that are not in our domain are x is not 1, x is not 4/3, and x is not -1. All right. So now we want to figure out, are these vertical asymptotes? Are these holes? So we could factor 6x squared minus 11x plus 4. Or we could just test these values. If we could synthetically divide it, that means it is a factor, which means we have that same thing on the top and the bottom, and it would cancel. So that would be something that's useful if this was maybe a cubic. Since it's not, let's go ahead and just try to factor the top. Okay, so we're looking for 2 numbers that multiply to be 24, add to be -11, so we know they're both negative. Oh, and we see here that -3, -8 works. And we were able to factor. So let's go ahead and rewrite this original function in a more neat way. Okay. So now we're looking. Can we cancel any same factors from the top and the bottom? And we see these kind of look the same. The signs are exactly the opposite, which means that if we had written our negative 3x plus 4 as negative 3x minus 4, we can see we definitely have these same factors. These will definitely cancel. And what that tells us is the function basically looks like, and I'll do kind of squiggle equals, the function basically looks like 2x minus 1 over x minus 1, that negative 1 left over in the denominator that we factored out, and x plus 1. Right, the function basically looks like that, but we took out this value. It looks like that, except there's a hole at 4/3. Okay. So what's left? What's left that's not allowed to be in the domain? Well, that means that we have vertical asymptotes at x equals 1 and x equals negative 1. Because those are the things left, and we don't have any matching terms on the top that we could just remove that bad factor from the top and the bottom so that the function still works. Okay, so just as a summary, our holes are the factors we can remove. And that kind of makes sense. When we remove these factors from the function, it creates a hole at that value. And then our vertical asymptotes are the factors that make the denominator 0. Right? Or really, they're we'll call them the remaining x values that make the denominator 0. And we get those from those remaining factors after we've canceled.